Hi, I'm Darren and welcome to Level Up EE Lab. No, I'm not starting to offer merch on my channel anytime soon. This is a very nice Christmas gift that I got from my family, and this is the first episode that I get to wear it. And I have been very busy over the holidays, but I finally got a chance in the last week to get back to working on that cell phone project. Let's check it out. In the first episode, I went through my grand ideas for this project, including showing this block diagram of all of the major elements I have planned. Now, on a project of this size, it can be really intimidating to decide where to begin. Temptation usually drives us to start working on the easiest parts first, and in this case that would be things like the LED display and the keypad. I call them the easy parts because they're what I like to call solvable problems. Meaning, even though I don't have fully worked out solutions yet, I've got clear paths for how to get there. The opposite end of the solvable problem spectrum in this case is the audio to RF and back to audio chain. As I said in the prior episode, there's lots of poor ideas out there for how to make that chain work, and I'd really like to come up with something better than what I've found so far. So that's where I'm going to start work. And it makes sense to reduce that chain to an even smaller initial problem, meaning eliminate the RF in the middle. In other words, solve the problem of converting the audio to digital and then back to audio. Once I have that problem solved and working well enough, I can then insert the RF in the middle and work that problem next. So let's take a look at the microphone. The raw output of a microphone is an AC signal that varies in amplitude and frequency, corresponding of course with the audio that it senses. We cannot feed that AC signal directly into the ADC input of the Nano for several reasons, starting with the fact that the microphone output typically has 0 DC offset. So approximately half of the signal is negative with respect to ground, and the ADC cannot sense below ground. So it needs to be DC shifted. It's also a very low level signal, and we'd only be using a tiny portion of the ADC's resolution. So it also needs to be amplified, but not over-amplified, otherwise we run into another problem, clipping, which would add a lot of distortion. So here comes the MAX 9814 to solve these problems. Looking at the spec sheet, this chip takes that raw microphone signal and outputs a conditioned signal that's DC centered at 1.25 volts. So there's our DC offset. It also amplifies the mic signal using automatic gain control, so no matter how loud the sound is, the output won't go below 0 volts or above about 2.5 volts, and it won't clip. So now with a signal that's between 0 and 2.5 volts, I've got something that will feed nicely into the Nano ADC, especially if I supply 3.3 volts to the A-ref pin to lower the ADC range. The final element that I need in this section is a low-pass filter. The bandwidth of the MAX 9814 is 20 kHz, which is much more than I need. For basic voice communication, around 3 to 4 kHz is plenty. But the bigger issue is the sampling rate of the ADC. Now, I haven't settled on one yet, but I know it's not going to be anywhere near 40 kHz, which is the absolute minimum needed to avoid aliasing issues. And once a signal is badly aliased, there's nothing you can do downstream to fix it. So I gotta have that low-pass filter in there. At this point, I suppose I could design and breadboard a simple low-pass filter circuit and start using that 9814 with the Nano and check it out. But that approach is fraught with a couple of difficulties, not the least of which is I wouldn't be able to get a consistent input signal and see what the output would look like, and I think I get tired pretty quickly of blabbing into that microphone. So a better solution is to use a signal generator like my Simpson here and generate a consistent and fixed set of signals and then test the output. Now this guy can certainly do variable amplitude, variable frequency, and an adjustable DC voltage offset. However, there's another problem here. I could easily overload the input of that Nano if I wasn't careful and fry that particular channel. So a safer method would be to come up with a simple op-amp buffer circuit between the Simpson and the Nano, and that's exactly what I'm going to do. Here's what that circuit looks like. I don't need a sophisticated op-amp here. The generic LMV358 will work just fine. It'll operate from a 3.3 volt single supply, its rail-to-rail output, and the rest of its specs are definitely compatible with this simple experiment. Like I covered earlier, I'll need an output that's DC biased at 1.25 volts and has an AC peak-to-peak range of about plus or minus 1 volt to properly simulate the 9814. In addition to using the Simpson to generate fixed frequency and amplitude tones for testing, I also want to try out the system with a repeatable and controllable audio source. And the easiest way to get that is to use the headphone output on my classic iPod. Some quick testing shows that a signal at approximately mid-volume peaks at around plus or minus 100 millivolts when driving a 50 ohm load on each channel. And my Simpson can easily generate a plus or minus 100 millivolts signal at fixed frequencies. So that'll be my input criteria. And that's really convenient because that means I only need 10 times gain in my inverting op-amp circuit, which is easily achievable with 10K and 100K for R7 and R8. Next up is to set the DC output bias, which I'm doing with R3 and R4 to pull the non-inverting input up a bit from ground so that it gets amplified to around 1.25 volts at the output. The final elements of interest are R2 and C2, which make up a low-pass filter with a 3 dB cutoff of around 4.8 kHz. R1 sets the input impedance to 50 ohms, and C1 is a DC blocking capacitor, which I've chosen to be 100 mic because it and R1 actually make up a high-pass filter, and I don't want it to appreciably attenuate the voice frequencies. Its 3 dB cutoff is 32 Hz, so that's low enough not to cause problems. Naturally, I did a quick simulation of this circuit, and here it is. The standard library doesn't have a model for the LMV358, but the LTC6082 appears to be a close enough equivalent. A transient analysis at an input frequency of 1 kHz shows I'm hitting my 1.25 volt DC offset close enough, and the amplitude is predicted to be just under a volt. And just for giggles, an AC analysis shows my two filters are rolling off as expected. Now, let's get to the lab and build and test this circuit. Okay, I've got this circuit built up and connected, and I'll do a little zoom in here on the breadboard so we can take a closer look at the circuit. Now, there's really not that much to it, and this is low enough frequency that I can do a breadboard. And the only little trick I had to do here is I whipped up my own little SMD adapter so I could put that little SOIC8 package on a piece of board with pins on it so I could put it on the breadboard, and so that worked out fine. Of course, I've got the Simpson right here providing the input signal, my trusty Heath 2718 power supply in the background providing the 3.3 volts, and then of course the signalant back here, I've got two signal traces shown on there, the input and the output. And I'll power it up here in a moment, but first I'm going to move the camera closer to the scope so we can really see what's going on. Okay, I moved the camera so we should be able to get a little better view of the scope now. It's always very tricky to try to video live any screen like on a scope because you just get so much glare and the camera kind of freaks out with the focus, but I think this should be legible enough to show my point. So right now I've got this set up so that the yellow signal, the one on the top, that's the input, and the purple one, that's the output. And input vertical scale, that's 100 millivolts per division, and the purple output is 1 volt per division. So right now there's no power to the circuit, so let me plug in the 3.3 volts DC and power it up, and we see the output shift up like it should. I'm expecting that DC bias, and if you look at the bottom of the screen, it's showing 1.39 volts, so that's close enough to my design nominal. So let me turn on this Simpson now and get that signal in there. And there we go. So again, the top is the input, it's the yellow, and the purple in the bottom is the output. So I'm showing about 200 millivolts peak to peak on the input, and I can of course adjust the gain on my Simpson to vary that. So put that at about 200 millivolts, and I'm getting about 2.04, looking at the wrong value here, 2.04 volts peak to peak on the output, or 1 volt amplitude. So that's exactly what I expect to get. So I think this circuit's going to work just fine. And of course, one last thing here, as I increase the frequency, we can start to see the output start to taper off as that filter network is starting to kick in. So at this point, time to hook it up to the Nano and see what I get when I digitize it. Okay, what I did here, I put together a very simple program to try to take a look at the A to D conversion and see just how well my circuit is working when I apply the output to the A0 input on the Nano. So what I decided to do was to try to take a look at this on the serial monitor, and there's one big problem here. The serial monitor just cannot keep up with the fastest rate at which the Arduino can do its analog to digital conversion. So a workaround what I did here, I just created an array, in this case an array of 500 integers, and when the main loop is running, it's going to start at 0 on that array and just read the analog to digital conversion on A0 and just repeat as fast as possible. There's nothing else in that loop except for that if-then comparison here. Now, once the count gets up to the array size, it'll do something different. It'll take whatever in that array and then spit it out on the serial port, and then I can examine it. And then it'll reset the counter back down to 0 and start again. And I did put a 1-second delay in there just so there's a little bit of pause before it repeats the cycle. I figured that's probably my best shot to really see what's the fastest rate that the Arduino can do this analog to digital conversion. Now, according to the online documentation, it says that the maximum rate is approximately 10 kilohertz. So, of course, that assumes I would think that there's not much else that the Atmega is doing during that time period. Anything else you add, such as if I tried to spit out the data in real time on the serial port, it's just going to bog it down, and I'm not going to get that sample rate. So I think this is probably my best way to get a little window, little snapshot, if you will, of what's happening here. And I think a 500 sample window taken every second or so will give me a good idea of what's happening. And one more quick item, I did put some code in here so I could turn on and turn off that particular logic in the code. So if I type in R on the serial command here down at the bottom of the serial monitor, it starts the data acquisition and will spit out the values, and just entering S for stop will stop it. That way I can pause whatever I'm seeing. So at this point, what I'm going to do, I've got the Nano plugged in and running, and I'll turn on the Simpson. And I'm going to set the frequency input to the Nano to about 1 kilohertz. That's my, I guess, basic test frequency. And we'll get it going here. So I'll enter R for run. And it's kind of hard to see what's going on here because it's just spitting out numbers. But of course, what I can do is turn on the serial plotter. And I think what I'll do is put these in split screen so we can see both at the same time. There we go. So there you can see what that sampling is looking like. Now again, this is a 1 kilohertz signal, and what I want to do is pause it at this point. So enter S to stop. And what I can do is scroll through these values, and if I really wanted to determine what the apparent sample rate is, I could look for the minimum, which would be, say, down here on 1 cycle, and then watch when it goes to a maximum and then back to a minimum. And that give me at least a crude idea of what the actual sample rate is. And doing that, stepping through here, I've done that offline, and it looks like I'm getting about 10 samples per period on this 1 kilohertz wave. So 10 samples over 1 kilohertz is approximately 10 kilohertz sample rate. So that makes sense that that's what I would expect to see here if, in fact, the 328 is running as fast as it can without any other inefficient loss of clock cycles to give me what it says is about a 10 kilohertz sample rate for that A to D conversion. Let's see now what happens when I increase the frequency of this signal. And as a refresher, I've got a signal here on screen that's frozen. It's around 1 kilohertz. Now, if you recall what I said earlier in this episode, I've set that single pole filter to have a 3 dB roll-off at about 4.8 kilohertz, and I'm really right on the edge of the Nyquist criteria here. If you remember the basics, that if you're sampling, in this case at 10 kilohertz, then the frequency components in your signal can't exceed 5 kilohertz, otherwise you're going to run into aliasing problems. And I can actually see that happening here, which gives me some concern, which I'll talk about in a moment after I demonstrate it. So let me turn this back on, type R here, and we see the waveform marching across the screen. In fact, I'm going to drag this over here, make it more full screen. Now watch what happens as I increase the frequency. So I'm going to double it up to 2 kilohertz, and we see that we're already not capturing as much of the signals because we're only getting roughly 5 data points per period instead of 10. And we start to see some distortion there. And as I go even higher, it almost looks like the signal's modulated because we're just not getting enough data points per period. And if I get right up close to the Nyquist criteria, oh my gosh, look what's happening. I'm getting a really funky almost modulation, like I say, on that signal. There's a very low frequency component there that's not real. That's not part of it. It's just errors coming from data acquisition. And if I exceed around 5 kilohertz, let's get this up above the Nyquist criteria, that distortion looks like it's smoothing out, but what's happening is I'm getting an erroneous signal. Now I'm up around 8 kilohertz now, and look, it's reporting out that looks like I have a sine wave that is at a much lower frequency. Now, of course, the amplitude of this has changed because my filter has knocked down the magnitude of it, but probably not enough. By the time I get up here to near 10 kilohertz, near my sample frequency, I'm really getting some bizarre behavior. So what to do about this? Well, let me proceed to dial this back down to 1 kilohertz. So a couple of things. One, it might not be an issue. The amount of higher frequency components that are actually in the speech might not create as much distortion as I think, and it may sound just fine. That'll be what I'll find out when I actually hook it up, throw the whole chain and try it out. I might need a more aggressive filter. Right now, I've only got a 1-pole filter there, so I might need something with more poles that will help roll that off faster. In worst case, I might be fighting a losing battle here. This 10 kilohertz sample rate might just be way too low, and especially, like I say, when I throw in other elements in the code that the microcontroller rather, is going to have to deal with, I may end up with a significantly lower than 10 kilohertz sample rate. So I have any choice, I might have to go to a more higher power microcontroller here, or something that can give me a higher sample rate. But we'll see when I get to that point in the project and actually get the entire audio chain connected and see what it sounds like. That's it for today's episode. Up next, I'll be working on the digital to analog conversion, and for the first time, I'll be able to see if this Nano with the 328p microcontroller is really up to the task of doing the audio to digital to audio conversion and yield an effective sample rate that gives me acceptable quality audio. Worst case, I'll be already changing to a different microcontroller on this project, so we'll see. So as always, I thank you for watching my channel and watching these projects that I find interesting. So until next time, bye for now.